Section 4.6 discusses the Poisson distribution, which takes a little different set of circumstances and gives us a good way to look at probability when instead of a fixed number of trials, we have a known average over some kind of an interval. So the interval can kind of take several different shapes. It could be a time interval, and in fact that's probably the most common example. But it could also be a geographic area, or it could be maybe that we're talking about something mathematical and the interval is actually a numerical interval. Lots of different possibilities, but the formula for the Poisson here, you'll notice, uses mu, which is that mean, and E, which is Euler's number, or the natural base E, and then X is going to be the number that we're trying to find the probability for. What's the probability of exactly X occurrences? So very different formula than we had for binomial. Binomial required n, the number of trials, but here we don't have that. We just have a mean. So the requirements, just like with binomial, there are some requirements, and the first is that we have to have these occurrences spread out over some interval. Okay, could be a day, could be a year, could be a square mile. Could be lots of different things, but it has to be spread out over some interval. The occurrences must be random. They have to be independent, so the outcome of one doesn't affect the outcome of another. And then they need to be uniformly distributed over the interval. So you can't have an interval from 0 to 10, but all of your values occur between 0 and 2. That interval would not be appropriate. Okay, so things have to be distributed throughout the interval. Here at the bottom you see the notation that we use. This says X is distributed as a Poisson with a given mean. Okay, so you only need one variable for the Poisson, and that is I shouldn't say variable. You only need one parameter, and that is the mean. All right, so just again to point out some differences between the Poisson and the binomial. Poisson is not affected by the sample size, okay, the number of trials. It's only mu, it's only the mean. Binomials do have a fixed number of trials, and so you can't, the Poisson's a little bit like geometric in that there's really no limit to the number of trials, so it could go forever. So fixed trials for binomial, no fixed trials for Poisson. That's really the big difference. All right, for our first example, this is one out of an old textbook. I just kind of like it because it gives us a different example than a time interval. During World War II, we have 535 V1 buzz bombs that fell on an area of 576 regions of 0.25 square kilometers in South London. So these quarter square kilometers are not necessarily blocks or anything laid out physically in the city, but what we've done is we've kind of gone back and looked at the distribution of these bombs and where they fell, and we've divided that area of London up into 576 regions. Okay, so we want to know what's the probability of 2 falling in the same region, and then how many regions could expect to get hit by 2 bombs. So we're going to switch over to the document camera so that I can show you both what I'm writing down and what I'm punching into the calculator to help you with this example. In example 1, we have 535 of these V1 bombs that are falling in 576 regions of London. So what we want to do is we want to find out the average per region, and we're going to do that by dividing. Okay, 535 divided by 576 gives us 0.9288. All right, so our mean is 0.9288. That's our mu for this one, because that's the average number of bombs per region. So now we want to know what is the probability of 2 bombs falling in the same region. So part A, X is 2. We want to know what's the probability, I should write it like this, what's the probability that X is 2? So we're going to use the Poisson PDF, which is second vars, and then it's pretty close to the bottom. I think it's quicker to go up, which brings you to the bottom of the list, and then go up. So Poisson PDF, our mean is 0.9288. By the way, your calculator calls this lambda instead of mu. I don't know why, but the mu that every textbook I've ever seen is the mean, and this lambda in the calculator is also the mean. I don't know why it's a different letter. All right, so the probability is 0.1704. So I don't think you guys can, maybe you can see my calculator screen, hope so, but that's how we do part A. Part B says, how many regions can expect to take 2 bombs? How many regions are likely to get hit by 2? Well, basically what we have to do here is we have to take the probability of getting hit by 2 and multiply it by the number of regions that there are, which is 576. So we'll take that and multiply by 576. We get 98.14. So I'm going to say approximately 98 regions can expect to be hit by 2 bombs. Next example is out of the book, 4.29. And Leah has an answering machine. She gets about 6 calls between 8 a.m. and 10 a.m. And we want to know, what's the probability that Leah receives more than 1 call in the next 15 minutes? This example has a good, it's a good example of how we have to be careful of what the interval is that we're actually using for the calculation, because we've been given 2 different intervals here, from 8 a.m. to 10 a.m. and then 15 minutes. So we'll switch back and do this one on the document camera as well. In example 4.29, we're told that Leah has an answering machine that gets about 6 calls between 8 a.m. and 10 a.m. So that's a 2-hour time window. What is the probability that Leah receives more than 1 call in the next 15 minutes? So because the question is about a 15-minute interval, that's what we need mu to be in terms of. So if we know that we have 6 calls over a 2-hour span, right? But I don't want to divide by 2 here. I actually want to divide by the number of 15-minute chunks, 15-minute intervals there are in those 2 hours, right? Well, 15 minutes is a quarter of an hour, so there's 4 per hour, and since we're talking about 2 hours, that's 8 total 15-minute chunks, 15-minute intervals. So that means that our mean is 0.75 for this one. Okay, that's 0.75 calls per 15 minutes. So we want to know, what's the probability that she gets more than 1? All right, well, more than 1 is going to be kind of hard to calculate, right? Because there's no upper limit for that. So instead, we do the easy thing. We're going to do 1 minus the probability that she gets 0 and the probability that she gets 1, right? Because greater than 1 leaves out getting 0 or 1. So if I find those, I can do 1 minus that, and that will give me the correct probability. So we'll go back to our distributions menu, second vars. We go Poisson PDF. This time our mu is 0.75, and we're going to do 0 first, and we get 0.47236. And then we'll do it again. And actually, just as a little note for speeding things up a little bit, if you've already done one of these Poisson PDFs and you hit second enter, it brings up the last thing that you did, and all we got to do is change the 0 to a 1, and then we can recalculate. So this time we get 0.3543, I guess 27. I'll go 35427. That way I keep the same number of decimals. All right, so now I just need to subtract these. So 1 minus that one minus that one gives me 0.1736, let's say. So the probability that x is greater than 1 is that, 0.1736. Before we do another example, I just want to point out the standard deviation for the Poisson. One of the interesting things about Poisson is that the mean and the variance are always the same. So we talked a little bit about the variance. I didn't give you much on it, but the key is the variance is the standard deviation squared. And we use the variance in a couple of more advanced calculations. So we haven't really talked much about it yet, but the standard deviation we've talked about that a lot. So the standard deviation is a real simple formula for Poisson. It's just the square root of the mean. All right. Again, one other thing for the last example, we've dealt with quite a few questions so far that have at most or at least, less than, greater than. And so there is a slightly simpler way to calculate these than just doing a bunch of PDFs and adding them up. And I have hesitated to share this with my regular stats classes because it's very easy to get confused. But I think you guys are probably a little more advanced. Well, you're definitely a little more advanced than my typical stats class. So I think you guys will be fine. I just want to point out that in each of the functions that we've used in the calculator, you may have noticed that there's like a binom PDF and then a binom CDF. There's a geomet PDF and a geomet CDF. And so far, all I've told you to use is the PDF. But that CDF function stands for cumulative density function. And basically what it does is it gives you all of the probabilities less than or equal to the X value that you put in. Okay, so it's doing the addition for you. It's adding it all up. So if you particularly for large numbers like the next example, if you have a less than kind of question and the number is pretty big, less than 100, well, you don't want to add up 100 values. So the CDF is definitely the way to go on that. So on our next example, which is 4.31, we will look at how that CDF function can help us, particularly on part C. All right, so we'll switch over to the document camera. Example 4.31, which is actually out of the textbook as Try It 4.31. I apologize for taking a Try It problem that you might have wanted to do in Perusall, but this one was about Atlanta Airport, the Hartsfield-Jackson Airport. So I thought, it might be worth doing just because it's kind of relevant to our lives in some cases. So it says that on average there are 2,500 arrivals and departures each day. How many airplanes arrive and depart per hour? So we've got 2,500 planes and obviously 24 hours in a day. So that gives us an average per hour of 104.1. I think I'm going to go 167. We'll just do it 3 decimals. That should be enough, I think. That's part A. What's the mean? So this is our mean, okay, per hour, because the next couple questions are going to be asked. What's the probability of this in 1 hour? Okay, so that's our mean is going to be in terms of 1 hour. What is the probability that there are exactly 100 arrivals and departures in 1 hour? So the probability of exactly 100. Okay, so this is going to take us back to the Poisson PDF. This time our mean is 104.167, and our X value is 100, and we get 0.03663. Okay, so even though the mean is 104, there's only like a 3.5% chance that there will be exactly 100 flights in a given hour. So the next question is probably a little more relevant. It says, what's the probability that there are at most 100 arrivals and departures in 1 hour? So this changes things. Now we're dealing with, basically less than or equal to 100 flights. So this is where the CDF that I mentioned a minute ago in the video, this is where this is going to come in handy, okay? Because without it, we'd have to do Poisson PDF for 0 through 100 and add all of that up ourselves, which would be terrible. That would be a massive waste of time. I wouldn't want to do that. So instead, we're going to use Poisson CDF, which is right below PDF. And we're going to enter in our mean, 104.167, and our X value this time is 100, and we hit paste. We get 0.36505. I think I'll round it to 0.365. So 36% of the time there will be less than 100 flights, or less than or equal to 100 flights in any given hour coming in and out of Hartsfield. So be careful using the PDF and CDF functions in the calculator. They're very close together in the menus, and they look identical when you're typing numbers in. Okay, I mean, the only difference, if you look closely, the only difference is up at the very top in that dark box there, it says Poisson PDF, versus if you do the other one, it says Poisson CDF. But it's very easy to miss which one you're working on. So they look exactly the same when you're typing numbers in. So be very careful to choose the correct one. If you're dealing with just one, the probability of exactly one thing, use the PDF, or maybe one or two things. Okay, it's not hard to add a couple of things together. Use CDF if it's a less than or a greater than, and the numbers are too big to add them all up. Okay, but be careful which one you're using. Okay, it's really easy to make mistakes there. For homework, you've got just a few problems out of the practice section that I think will be sufficient to give you the practice you need for the Poisson distribution. And then hopefully your quiz on Friday will go well. And if you have any questions about anything before then, please don't hesitate to send me an email, or you can send me a message on Classroom. So thank you very much. Hope you have a great day.